Hello, in this video I'm gonna explain how the MLACCD cooling channel software works. So from the website, you can download the zip file containing the MLACCD.zip, which is the cooling channel design software in our research group. And to decompress it, you can contact our research group to get the passcode. After you decompress it, you will see something like this. And to execute the software, you can double-click the disk menu. And then you can click the model CGUI-EXE. So this is the command window for this software, and you won't need to do anything for this command window. Just need to wait for a few seconds until the software pops up, and you can leave this window here for the extra communication from the software to the user. And the software will ask you to upload the upper and lower cooling surface and specify the size of the part in either X and Y axis. So make sure that you also properly align the part in your own CAD design, CAD design software. So basically, you're gonna have a larger part dimensions in the X axis and smaller dimensions in the Y axis. And please do not align the part in the Z axis because that will cause the calculation error. So this is some cooling surface example cooling surface in our own software library. So I'm gonna import these two cooling surface to the software to let you see how this software performs. So in your own case, you will need to specify the file directory. And for the size of the surface, I can estimate with the CAD software. So in your own case, you can also give a rough estimation. This doesn't need to be very precise. It is used to calculate the accuracy of the cooling channels. I mean the rough calculation of the accuracy. So accuracy level. So then we can upload and click next, and you'll see something like this. So these are the currently 3 topology we support. If you have another topology that you need or you think is interesting, you can email us and we can develop the different topology in the future. And in this case, I'm gonna select the zigzag topology. But actually, these 3 topology will all works for this cooling surface. So I click zigzag. And for the TBM accuracy, I will just select some numbers like 2 to make this simulation faster. In your own case, if you want very precise level of the TBM accuracy, you can drag it all the way to 10. But the simulation time will actually be longer. So for this, I will just call this output file.stl. So what will be generated is one STL file containing all the solid cooling channels design. You can use that for the the injection mold design. It will also generate an Excel file containing all the coordinates of the line segment for the cooling channels that you can use for the simulation or research purposes. And then I will just click Run. So you see that you have the progress bar and you have something illustrating what is currently done by the software. You can also see the commander window saying the same thing but in a simpler format. So this is something you will expect from 2 very different cooling surface. If you see some the warning message like this, but the difference between the lengths is very small or relatively small like this, then this is fine. But if you get something like 1600 and for this is 000, then you're probably in some trouble. So you will either need to check your design of the cooling surface to see whether you really get the cooling surface that matches each other. And then you will see that the machine learning optimization of the design parameters is taking place. So if you type in some target temperature that does not exist in our database, that is fine. That just allows the extra calculation time for the and we will see from the commander window that we will calculate and enlarge our temperature database first, and then do the machine learning optimization process. So that in the second time, you won't need to do the machine learning temperature prediction in your following calculations. So now you see that our software is close to the completion. So this is something previously executed from the developer window. It is extra. And then afterwards, something will pop up in the commander window that says the coordinates of the control points. You can just ignore it, but for some researchers, you can use it to directly put in your in your compiler to design your cooling channels. That I leave for the users to use, but for most of the users, it won't be very necessary. And then now the cooling channels and the cooling channel control line coordinates is generated. And this is a Excel file that contains all the line segments of the cooling channels. You see that there is 117 lines, and here is the coordinates of the line segments. And this is the output cooling channels. We can drag it to here for yeah. So basically, this is the cooling channels, and you will see that if you have very traditional conformal cooling channels, the cooling channel will conform to this surface very nicely. But for our cooling channels, it don't conform to it not only conforms to the part surface geometry, but also conforms to the part thickness distribution. So for instance, the thickness here is smaller, so we don't necessarily conform to the part surface geometry, but we have a larger part cooling channel pitch to the part surface distance, so that we will get a uniform part temperature distribution for this. So this is the cooling channel generated, and you will see that even for here, the width for the cooling channels here is actually very smaller, because here the thickness here is different. Is different from elsewhere. You can also select other cooling channel topologies if you want, but now I will explain the other features of this software. So I'm gonna rerun this software to see how does the temperature being imported into the database. So if you click the spiral, this time I'm gonna select the spiral. So as you can see that for the spiral cooling channels, you will have more information to be added. The safe path, you can always specify your own safe path, but for this time I will say output file 2.stl. So this is the start point coordinate. So you're gonna specify where your spiral cooling channel start. For this, I will just type 0. And this is a spiral angle resolution. This angle resolution is specified here. So in the real case, you get a cooling channel that contains a line segment like this. So if you specify a very large spiral angle resolution, you will get a very spiral cooling channel. But in this case, for illustration purpose, I will just say 5 or 6. So for this time, I'm gonna type in some target temperature that does not exist in our database. For example, I can type in something like 15 degrees, just for illustration purposes. Or 15 is too small, maybe 25. And if I click run, you see that this is the process of generating the cooling the additional temperatures for our database. So you can see from the command window, and this is actually your TensorFlow. It starts machine learning process. So here is smaller because it probably reached something that is challenging to calculate. This actually takes some time. It usually takes 5 minutes for the most of the computers, but for some temperatures it may be slower. For example, if you type in a very high temperature, then this calculation will be slower because for every thickness, it requires for the for loop for the temperature for the design parameters calculation. So I'm gonna skip this and see what if we type in the a usual temperature that the spiral cooling channels can be quickly generated. This time I'm gonna call it out spiral. Almost 39, 0, 0, and 6. So it starts optimization of the design parameter process. So I'm gonna escape this process until it's finished. So now the simulation is close to complete. And then it's the generation of the mesh. So now we can see our output file for the spiral cooling channels. So these are the coordinates of the points. It's not that much because the cooling channel is we only specify 6 for the spiral angle resolution. And then this is the output spiral cooling channels. As you can see that the cooling channels here is even further from the cooling surface because the distance here is smaller. And if you specify a larger value of the spiral angle resolution, then this will be much smoother. So now I will finally explain the CPS cooling channels from our software. So this time, I'm gonna choose the CPS test surfaces. So to visualize these surfaces, you can use your own CAD software. So this is the CPS cooling surfaces, example cooling surfaces we have. So the rough dimensions of these cooling surfaces is 100 in both directions. For this one, I'm gonna call it output CPS. So this is something that can show up when something goes wrong. So it says no such file or directory CPS test1.stl. So this is basically because I type in the wrong name. So I forgot to type this slash. So now I will do it again. So now the program is correctly running. So it's generating the point cloud first. And then it's gonna start the machine learning process. So you will see something like this because the temperature I typed in does not exist in the database. And I will skip the database expansion process because this takes time. So now is the start of the optimization process because I skipped the database expansion previously. And then I'm gonna escape this as well. So now the optimization is close to finish. And afterwards, we will see some mesh generation process. So I'm gonna skip this whole process until this is finished. So now the mesh is generated. You can see from the Excel that the CPS requires much more number of the line segment to generate the cooling channels. And if we drag this here, we will see the cooling channels. So this takes some time because the match for the cooling channels is very large. Yeah, and this is the finally generated cooling channels. So this cooling channels you can also see from our user manual. So this is the finally generated the CPS cooling channels. And this is the end of this video. So hope you found it helpful for using this software. And thank you so much.